Today we're going to study the thin film interference. Let's see, for example, we have some medium has an index n1. Remember, the index n1 is equal to the speed of light divided by the speed of light. This is c, is the speed of light in a vacuum, divided by the speed of light in the medium n1. And then we have another medium here. This is n2. And n2 is the speed of light in a vacuum divided by the speed of light in that medium 2. And then we have n3. And the same thing, n3 is c over v3. Now let's assume n3 is bigger than n2 and n2 is bigger than n1. So this index here is high. The light slows down in this medium here more than it slows down in n2, more than n1. n1 we can say n1 is just air. So actually n1 is closer to 1 because the speed of light in air is closer to the speed of light in a vacuum. Now let's see, we have some ray. This is a ray of light coming in from the sun, for example. Here is the sun and the ray is coming in. This ray will hit the surface. It's going to hit the surface. Some of the light will reflect with the same angle. This is the angle theta, that's angle theta. And some of the light will refract, will go through the medium 2 like that. And then will hit this surface here where medium 3 is. And let me put here, this light will reflect. Now, when the light reflects from the surface with if n2 is a higher index than n1, the light that's gonna be reflected is gonna be shifted by 180 degrees or shifted by pi. What does that mean? We need to understand this before we move on. So let's take, for example, a rope. We have a rope, and this rope is loosely attached to this wire. We have a ring, and the rope is attached like that. This is a rope, and we have a ring, and this ring can slide with no frequency, with no friction, down and up the wire. So if we wiggle the rope, let's see, we're gonna wiggle it. If we wiggle it, it's gonna create a wave like this. Now, if this end is loose, is not fixed, when the wave bounces back, let's see, the wave is coming this way. When it bounces back, it's gonna bounce with the same phase like that. That's how it's gonna bounce back, because this is loose. So it's gonna go up and then go back to that location and come back in. Now, if the end of the rope is fixed, now here, this is, I would put here loose, and here the end is fixed. I put here end loose, here end fixed. Now what's gonna happen? Here is the wave coming in, and this is fixed. So what it's gonna do, the wave will bounce back like this. So this is a wave that's coming in, and the other one that's bouncing back. So you see how the bump goes with the dip. What was a dip becomes a bump, which means the wave got shifted. Now we still, some of the students might not understand this. So I need to clear this up. Let me make it clear. I have to move the paper up so you guys can see. Okay, so now if I have a wave coming in this way, okay, and another wave in phase Let me make it red. This wave is red as in phase. So these two waves are in phase. Okay. Now I'm gonna make the red wave shift by 180. So here is the green wave. And look what's gonna happen to this is gonna be shifted. It's gonna move to the right this way. So it's gonna come over here and then go like that. So it got shifted by half wavelength. This is pi, and pi is 180 degrees. So I put here 180 degrees. So when the end is fixed, the wave that bounces back gets shifted by 180 degrees. Now, if we look at this picture here, top picture here, okay, the wave was coming in, is going to encounter this medium with N2. And remember, N2 is bigger than N3. Or N2 is bigger than N1. So the light, since the index here of N2 is higher than N1, it's like the light get fixed somewhat at that point, and then it reflects with the shift. So here, reflection, we have 180 degrees shift here. Now, this reflected got shifted by 180. Now, the refracted light will go into the medium. It's going to encounter medium N3. It's going to reflect like that. Now, if it gets reflected, look at N3 is bigger than N2. So it's going to also shift by 180 degrees. So this one is shifted by 180. This one is also shifted by 180. You see, this one that came in is not shifted. But this one gets shifted because N3 is bigger than N2. And then some of the light will get shifted, but some of the light will refract. So we have refraction, go like that. I made the angle so small because N3 is bigger than N2. Now what's going to happen here, this light that got reflected here is going to refract like that. Now, these reflected light and this refracted light can meet and interfere, this and that. Now, if they meet and interfere, remember, they're shifted. This one is shifted 180, but this one also is shifted 180. When it comes out here, it stays shifted 180. So both of them got shifted 180, so they're going to be in phase. So this and this wave and that wave are in phase. Now what do? We can say that, let me write down here. All right. 2, I put here, m lambda. M is the number of waves inside here, the number of waves going along the path of light that I drew here in the red, is equal. Now these angles are so small that I can consider this path, I can consider it D. This one is D and that one is 2D, so I put 2Ds. So m lambda is 2Ds. But the wave here, I need to put n lambda n2, because this lambda n2 is equal to lambda over n2. So the wave here, it's going to shorten, okay, by this index. So the wave that's traveling here, we call it L lambda n2 here. So my equation becomes this: m lambda over n2 is equal to 2d. Let me move up, sorry. Move up like this. Okay, m lambda. This m is a number of waves here. You count them, 1, 2, 3, the number of waves. Lambda is the wavelength, original wavelength, but then we have to divide by n2 because it got inside here, is equal to this 2d. So because these two are in phase, this equation is made for construction of light. Construction. Okay.